All right, let's get started. Hello, everyone. Good morning. My name is David Sankel, and this talk is about Zngur, Simplified C++ and Rust integration. I'm a principal scientist on the Software Technology Lab, which is a team that tries to figure out what the future of computing is going to be in software development and tries to guide that, help with training and tools and libraries and all kinds of neat stuff. Just a quick note that Adobe has and will have open positions. If you are interested in a potential change or joining Adobe, please use this QR code to check out what we got. I'll show this again later on when we get near the end. Okay, so back into the content. Why is Rust and C++ interop interesting? We're at a C++ conference. Now we're talking about some Rust C++ interop stuff. What's going on here? Well, on balance, in my opinion, Rust is just better technology than C++ for most applications where C++ is currently being used. Certainly not all, but most. The reasons are there are a few of them. So the first one is that Rust has powerful language mechanisms. You have enums, which are language-based variants. You have pattern matching. You have traits, which are kind of like checked exceptions. You also have excellent procedural macro-driven libraries. So if you want to do command line parsing and have that all automated for you, just do the data structure that you want to use. You can do that. You have very mature libraries in Rust that do that. Obviously in C++, we're going to get that eventually, something like that. There's also very compelling engineering features. Documentation technology is very good. You can put your tests right next to your code in a very non-hacked up way. And there's excellent tooling in this when we talk about package systems and so on. And the ergonomics of the language are just superb when you compare it to C++ and languages of that age. It's just very easy to use, comparatively speaking, and people like it. So that's just on the tech side, what my opinion is in terms of Rust being just better tech for most applications that C++ is currently being used. But there's also trends in programming languages. If you take a look at the data, which is something that I do often, you can see that there are trends in programming languages, and there is a growing percentage or growing number of C++ developers that are also using Rust as part of their day-to-day workflows. So if you look here, you can see in 2019, it was more of like a niche thing, maybe somewhere around 6% of C++ users were also using Rust. But there's been a drastic change, and we've kind of leveled out to about, like 21% in 2023 and 2024 of C++ developers that are also using Rust. So it's just a reality that Rust is becoming a more and more typical part of a C++ developer's workflow. Looking at it from a demographic perspective, here what you see in the orange is the percentage of developers, all developers, that want to use Rust. And what you see is in the blue is the percentage of all developers that want to use C++. And as you can see that when you move from the right to the left, if you're looking at the orange line, you can see there's just an increasing number of people, especially newer engineers, who are desiring to use Rust as a language they want to like professionally program in. When you look at C++, you can see that it kind of like drops down until you're between ages 35 and 44. And then it kind of increases again when you're in the 18 and 24 range. There's a spike. I don't know why. But clearly, if you're trying to hire up a professional development team and you're thinking about what language you're going to use, being able to staff a team of engineers is an important part of the decision-making process. And so based on this data, it's looking like it's increasingly going to be an easier time to be able to hire a Rust developer than it would be a C++ developer. Now, I don't have any data for people that are younger than 18. I wonder, are there anybody in the room that is younger than 18? Oh, You there. So what do you think about Rust and C++?
I think I don't have that much interest in learning C++, but I have a lot of interest in learning Rust. Seems pretty cool.
Okay, interesting. I saw another hand over here.
I agree with her. I think that C++ is Rust is a lot easier.
Cool. Well, there you have it. We have the data.
Unbiased data.
I'm biased, just people in the room randomly.
I mean, here we'd expect, if it's biased, it would be the other way. So,
Yeah.
Interesting. So, moving swiftly on, there's also evolving expectations for software safety, right? And this is a big one of the motivators that has come to prominence lately. So, software developers generally want to ensure their customers are secure against malicious exploitation, right? That's extremely important. And adoption of memory-safe languages has the potential to reduce vulnerabilities by 70% for newly created code. And this is based on the data that we've seen internally at Adobe. It's also similar numbers for other companies that are out there that have published their information. And obviously that doesn't, get rid of all software vulnerabilities. There's another, 30% there. But that 70% that we know we can actually solve with a technology change. The other stuff, we don't have a great panacea that you can use for it. And so we've been seeing an increase in discussions about memory safety legislation. There was actually a bill that went through Congress, I think it was the House of Representatives, that included memory safety legislation in it, and it got removed when it met with the Senate version of the same bill. So that happened a couple of years ago in the United States. Obviously now, when it comes to the United States, who the hell knows what's going to happen? I mean, it's crazy. But Europe is maintaining some of their sanity, and they are pushing forward this kind of legislation. So it's just happening, right? So that's another important aspect. Well, then you might say, well, I mean, C++, it can be memory safe too, right? And there are some good improvements that are coming to C++ in this space. So in C++ 26, something we recently adopted is hardened standard library mode, where you can use a flag and get a hardened version of the standard library where it'll have less undefined behavior. And then there's also profiles, which will do something maybe someday to help mitigate risk. There's some promise there, but there's more questions than answers in terms of profiles right now. So maybe in the next 5 to 10 years, they'll have something solid to talk about. But on the other hand, safe C++, so this is Sean Baxter's proposal that actually carved out a safe subset of C++ that you can use, and it's actually make it a memory safe language. That proposal is not moving forward. And that was really the only thing that was viable to actually make C++ a memory safe language. So unfortunately, that's not happening. One of the things that I do see happening is there's safety theater going on, where people are saying hey, C++ is actually just as safe as other things, and we're going to do this and that, and it's really theater. There's actually we almost passed something in the standardization meeting, the most recent one, something that had no design, no implementation, but just to vote to move this to wording review, even though there's no wording for it, so that we can project that we're doing something about this, right? That is safety theater, right? And that's kind of disconcerting. So in my opinion, as someone that's been on the C++ Standardization Committee now for, I believe, over 10 years, there's little hope of C++ actually fundamentally addressing this in a way to where you'd want to use C++ where you need memory safety versus another language. I just don't see that happening. Okay, cool. So then you might just say, great, go use Rust, leave us alone, do your thing. But Rust by itself is not a solution, right? because we have all that C++ code which is out there, and there's a lot of it. So in Adobe Photoshop, which is one of our flagship products, there's over 30 million lines of C++ code, right? Good luck rewriting that in anything. Even with AI, I don't think it's going to happen while I'm alive. So Brian Cantwell-Smith estimated there's 100 billion lines of C++ in the world, and that was in 1997. Sage McHenry estimated there's 2.8 trillion lines of all code in 2020. These are just estimates, right? But that's more than the number of stars that there are in the Milky Way. So we're going to continue using that code, right? And we're not going to rewrite most of it. We're not going to rewrite more than like a pinch of that code. So we've got that. We've got these memory safe languages. We've got Rust. Like, what are we going to do? And this is where Rust C++ interop comes to the forefront. And the general feeling right now that I've gotten when I've talked with people is that Rust C++ interop is not really great, right? It's actually subpar. It's a pain in the neck to use. And we're going to look at that and the reasons for that. But what do we really want when it comes to C++ Rust interop? Ideally, we want a principled design, right? Not something hacked together that can just make it work, one work with the other. We'd like to have good ergonomics on both sides of the fence. We want to automate as much as we possibly can. We want a complete solution, right? Where you can't just, you have something and you just can't call it from the other side because it's an incomplete binding layer. Like, that's not going to work. And eminently, we want something which is practical, right? If we have a C++ Rust interop thing, which requires you to change your entire build system to something else, that's not going to get adopted, right? Not by the masses. So we need to have something which is going to be very practical. So let's talk about what we have right now, the current solutions. So we've got C API Gen. And I get the impression that this is what's most typically used. Although, I mean, there are large companies that are using some of these other ones, so I really don't know for sure. But the idea for this is that you write some C APIs, right? You have your just C functions, but you're writing the APIs in Rust. And then you automatically generate headers based on these C APIs. And I've done a bunch of this, so I have experience with it. The drawbacks are, the first one is that it requires you to build all this C++ scaffolding on the other end if you want to make a decent C++ library. This is a good way to interface Rust to C, but not as much for C++, because now you have C libraries you need to deal with. And if you're implementing these things, on the Rust side, you're dealing with lots of complicated, unsafe code when you're doing like the C layer stuff and doing allocations and pointers and stuff. And I can tell you that when we've taken C++ engineers, experts in C++, don't know very much about Rust, and we're like, okay, you need you to work on this. We need you to work on this interop layer. Their first impressions of Rust are the most gnarly, unsafe, like uncouth Rust you'd ever want to write, and it's hard. And so they walk away from it thinking like, this is just really complicated. And so that isn't working very well. Then you have to deal with callbacks and allocators in a C way, right? So if you pass a string over to Rust, then you also need to provide some kind of like deallocator for that string if Rust is taking the ownership of it. If you do callbacks, you need to do that void star trick that you used to always do with C. So it's not great. There's another thing out there called CXX. And this, I believe, is used heavily within Facebook, is my understanding. And the idea behind CXX is you write some bridge code in Rust, and then you make some smart C++ Rust translations. And in its own words, it is intentionally restrictive and opinionated. So this is like a subset solution where you can only represent some stuff on the interface layer. And it does lack some core functionality. For example, function pointers, it just doesn't have support for it. So for us, like when we looked into this for like one particular project, the lack of being able to send a callback or something over to the Rust side made it a non-starter. And then there's also AutoCXX, which automates most of the bridging code. So this will kind of parse your C++ and generate your Rust bindings automatically for that. There are a couple issues with it. The first one is that performance is a problem because anytime you're doing anything with a C++ object move over to the Rust side, it has to be allocated on the heap, so you have unique pointers everywhere, all over your interfaces. And when you're using things in Rust, C++ things in Rust, you're using pin everywhere. And if you're not familiar with pin, it's a way to ensure that something stays in the same memory location. And it's just not ergonomic on the Rust side. You generally don't have libraries that use pin extensively. It's just a very specialized use case, mostly in async. So having to have pin all over your code makes it not a great experience on the Rust side. So that's where we're at in terms of the current solutions that I'm aware of anyway. So I was really excited to find out about Zngur. So Zngur is created by a software developer named Hamedreza Kalbazi, and he is hailing from Tehran, Iran. So obviously getting him to come here and give a talk would be challenging. So in the words of Zngar's website, it says, it tries to expose arbitrary Rust types, methods, and functions while preserving its semantics and ergonomics as much as possible. Using Zngur, you can use arbitrary Rust crates in your C++ code as easily as using it in normal Rust code, and you can write idiomatic Rusty APIs for your C++ library inside C++. And that's going to be an important aspect of this particular solution, is that when you're doing gnarly interfacing between C++ and Rust, with this library, you're doing that in C++ as opposed to in Rust. And that has some important implications. So we said we wanted a principal design. What is the driving principle behind Zngur? And that is that C++ or Rust semantics is a subset of C++ semantics, right? That essentially C++ is more expressive than Rust is. And I'm going to show a few examples to kind of build the case for that being true. But this really drives a lot of the design decisions that happen in Zngur, and I think is what makes it as compelling as you'll see. So let's take an example of Rust errors. So when you have a Rust function and it can possibly have an error, what you do is you have a result type. It's just a different return type that kind of works like stood expected, where you have an OK, which carries a value, and you have an error, which carries a value. Well, you can represent that kind of thing in C++. Here's one way you could represent it. So on the right-hand side, you see struct OK, which is template type. You have struct error, which is a template type. And then using result is stood variant, OK, or error, right? It's just a variant, right? It's either one of these or one of these. We can represent that in C++. But if you look at the other way around, if you try to say C++ has exceptions, throw a stood runtime error, there's no representation of that in Rust. Rust cannot represent C++ exceptions at all, right? It isn't there. Another example is memcopy relocation. So on the Rust side, you see we're creating some type. We're using some type : new to create a new object of some type. And then we call this memReplace function, and this is a safe function that you can use. The first argument is a reference to X. The second argument is a new instance of this sum type. And what this function will do is it will take the memory at the new object and move it over the data at that memory and move it over to the data at where X is located. So it's like move, but we're just moving memory directly around without calling any kind of specialized move construction. Just move the memory. Can you represent that in C++? Well, it turns out you can. So in C++ 23, some type has to be trivially copyable. There aren't that many types that are trivially copyable, but trivially copyable means that you can memcopy that object to move it around to different locations. In C++ 26, I'm not sure if it's gotten plenary or not yet, but anticipated for C++ 26, we have the idea of trivially relocatable, which directly expresses that we want to be able to move objects with memory. Comment?
Yeah. you can't use memcopy with trivially relocatable because types with a signed v pointer on Apple ARM are trivially relocatable, and they require a special memcopy function that reassigns the v pointer when it's moved over.
Okay.
So it's trivially relocatable and not polymorphic on Apple ARM platforms.
Okay.
The condition for memcopy.
Great. Yep. And
But it can be done.
but the point is that it can be done, right? Yeah.
Yeah.
In the Rust code, is there a constraint on that memReplace function for an equivalent to trivial copyability?
No.
So this will work for any Rust type
Correct.
safely?
Safely.
Really? Wow.
Yep.
So I hope you don't mind my picking a small nit here. This is relevant to the last question. So that's valid for every Rust type because Rust doesn't support move constructors, right? You can't
Yes.
customize that. And so the expressivity difference really isn't in what code you can write and whether you can express this, it's whether you can express a non-trivial move.
Right. And we'll get
So-
to that in the next slide, actually.
So
yeah.
I mean, I would say like the equivalent C++ to this Rust is just the one that does move construction.
Well, maybe. I mean, the thing is, if you have a type which is memcopy movable, you can memcopy move it in C++.
Right, but the semantics are the same. So you're talking about expressing semantics, right? This is just like an efficiency hack that you can do with some C++. So this is just a small nit about like where is the expressivity difference. I agree that C++ is more expressive. I think it's easier to see that C++ supports custom move operations and Rust doesn't. That's sort of an easier thing to illustrate. That's all.
Okay.
This might be a trivial question, but how does this particular code interact with destructors in C++, or I think it's called drop in Rust?
So memReplace actually returns the old object.
Okay.
Yeah.
Does C++ not do that?
So let's look at the C++ code just so we understand how we're doing the equivalent on the right-hand side here. So here we create an object of some type, and here we create some data somewhere that has the right alignment for that type. It has the right size for that type. Here we use inPlaceNew to create an object at that memory location. And here we use std_memcopy to move this over to the other object. So this is totally fine as long as some type meets those requirements with the additional caveat that Jonathan mentioned.
Don't you need to not run the destructor on X now?
Why not?
You copied it.
Right, but that'll cause the destructors to run twice.
Nope. See, the thing is, when I did the inPlaceNew
Yeah.
for x_new,
Yep.
that destructor was never going to run. Yeah. All right. So now talking about the other direction, the general moves. So in C++, we have some type here, and it has the move constructor. It has a custom move assignment operator. And in its data members, we have an array of a buffer, and you have some kind of a int pointer which points to something in that buffer. Like if we do a memcopy of this from one place to another place, that selection pointer is going to be pointing to the old object's memory location, right? So it's not going to be valid. So that's why you need to have, that's why you'd have these like custom move operations. And in Rust, there's no equivalent for this. You don't have user-defined moves. Doesn't exist, right? So yeah, moves in Rust, unlike C++, are always memcopy. Rust uses moves in assignment, passing arguments by value, returning values from functions, and with a small note that actual moves may be optimized out, right, in Rust, but and at least semantically, the moves are potentially happening. And this has a really important implication when we're talking about Rust C++ interop. It basically means that C++ objects cannot be put on the Rust stack in general, right? because you put it on the Rust stack, and as soon as you like call a function, it does that mem move. Now you got an invalid object. So it's all kind of screwed up. So so we're always going to need some kind of indirection when we're talking about C++ objects in Rust. Law of exclusivity. This is another expressivity issue. So in C++, we have a function here. It takes in 2 int references. And in main, we create int I equal to 3, and we call f with I twice. Totally valid C++ code, not necessarily undefined behavior. You're not seeing the inside of f. Generally, it's not a good practice to do this kind of aliasing thing, but you can express it, right? You can express it in C++. If you try something like this in Rust, so here we have f with 2 mutable references of I32, that's just 32-bit ints. And in your main function, you have let a equal 3, and you try to call f with 2 references to a, you're going to get an error. It's going to say, sorry, you can't do that because you can only have 1 mutable reference to an object at any given time. So this kind of code, you cannot express it in Rust. So hopefully building up this idea that Rust semantics are really a subset of the C++ semantics. So everything in Rust that you can express in Rust, you should be able to express it in C++, but not the other way around. So first observation I just made. When it comes to Rust's complexity or its apparent complexity, a lot of it lies in how that semantic is drawn inside of C++ semantics, right? They're trying as much as they can to remove the stuff that's probably wrong anyway in C++. That's where you have like law of exclusivity. And that can produce a lot of complexity.
Just a small thing. If there are people in the audience trying to evaluate Rust and they hear Rust is less expressive than C++, there's a word missing, right? It's safe Rust is less expressive than C++, right? You can make raw pointers in Rust and do all the C++ things, right? At least modulo being able to express custom move constructors and things like that, right? So yeah.
Yep, that's a good point. So implications of this are that using Rust code from C++ should be easy, if this is true. And using C++ code from Rust is going to be more challenging. That's what we'll see.
Is this a strict subset, or have you found like corners in the language where something in Rust that is not modelable in C++ yet?
I think that for the topic of interop, I haven't seen any like glaring counter examples to this. Like broader language, it's hard to make a claim. It's perfect.
Okay, so sorry. What about it? It occurs to me if you tried to pass something from C++ to a consuming Rust function, right? So it gets the arguments getting ownership is getting transferred, right? And it's a Rust object. Now C++, it seems, would try to run its destructor, right? But Rust has transferred its ownership, and that transfer of ownership doesn't allow that to happen. Am I wrong? Wouldn't you need like an empty state to move it to on the C++ side?
So we're going to get to how objects are like communicated between the two later on. So
okay,
let's pause that until then.
That's fine.
So it seems like that like using Rust from C++ should be easy. I think that's like still really nice because I think like the stuff you want to rewrite in Rust are like the parsing low-level stuff, and so it would make sense. And maybe you can design that in such a way that they don't need the C++ type. You just do that in pure Rust and call it from Rust, and then you don't have to worry about the other direction. And like
Yeah. I mean, and that's been my experience. And I think we'll see that using C++ from Rust is going to be more challenging, but it's not going to be that bad, really. So I think the questions are kind of getting ahead of the presentation a little bit at this point, so I'm going to drive forward a little bit. Let's take a look at the Zngur architecture. How does this thing work? So these are all files on your system here. The first thing to note is that at the top is this main.zng file. Okay, this is the Zngur file. This is defining all the stuff that's on the boundary layer between C and C++, or C++ and Rust. And this is a completely self-contained file. You take this file, you use this executable called Zngur, and it generates 3 files from it. Generated.h, generated.cpp, and generated.rs. Okay? Once you've generated these files, on the C++ side, you can compile all your C++ together. You've got generated.h, generated.cpp, all your other C++ sources. You compile those and get a bunch of object files. On the Rust side, you've got your generated.rs. You combine that with your other Rust sources. You can use cargo build to build a library. And then you get like a static library, or you can make dynamic library, whatever it is. Then you use your linker. And your linker will take your object files that you built with your C++ compiler, your library that you generated with your Rust stuff, and you get your executable at the end. Now, who's running this linker? It could be run through CMake, just using a C++ linker. It could also be run through Cargo if you wanted to do your linking that way. It doesn't really make a difference. This is just how it works. So looking at this Zngur file. So as I mentioned, it defines the interface boundary between C++ and Rust, self-contained. It does have Rust-like syntax. Like if you look over there and squint a little bit, those functions look a lot like Rust functions, which makes sense, right? Because if we have the subset semantics, you want to provide a Rust signature because that's the only thing that's going to be completely representable in Rust and C++. And this file is really strictly, it's just boilerplate that could be completely generated automatically, right? We're doing it by hand to learn the system, but this could be, there's no art to creating a Zngur file. And we'll look into the details of this in a sec. So let's start with the easier way. So we want to call Rust from C++, Rust to C++. So here we have a simple structure in Rust. So this is a pub struct person. It's kind of like a class in C++ or a struct. It has 2 fields, name, which is string, and age, which is unsigned 32-bit int. And then we have some operations on this. So in C++, you put your like your constructor and all of your member functions inside the class braces. And Rust, you always put them separately. Okay, so that's why this is a separate block defining these things. You have new, and this is the constructor essentially for the type. Rust doesn't have the idea of a special constructor. This is just a conventional name that you use for constructor, new. And then you have 2 of your member functions, name and age, which just return, these are just your getters, right? Returning self.name and self.age. And so the new, you can think of it kind of like a static function because it doesn't take a self parameter. And the other ones, they take a self parameter. So these are more like your member functions, these methods here. Once we have a Zngur file, you can just see that essentially this is just straightforward. You see the struct person over there on the left. On the right, you see we have a type called person inside of this crate. You see new, name, and age. Those are all reflected on the right-hand side in your Zngur file.
Is it 1 Zngur file per crate?
1 Zngur file per, I mean, not necessarily. Yeah.
So you can have more than 1 for a single crate?
Zngur file is just a file that you can run this command on, right? So, yeah. It's not even necessarily associated with a crate. It's just a file. Any other questions before I move forward?
The layout.
We'll cover that. Yep. Okay. So we take this Zngur file, and let's just look at the C++ code that it generates, right? We run generate on it, we get some C++. So you look on the right, we see our generated.h, we see a class person that got created. Okay, no big surprise there. But you might be surprised at seeing there's that person constructor with no arguments. So Rust objects can always be created uninitialized. You just create an object, it's uninitialized, and the Rust compiler guarantees statically that you are initializing it before it's used, which is kind of nice. In C++, it keeps that idea of you can create an object in uninitialized state. So you have this constructor, this empty constructor. You create an uninitialized object. The only difference in C++ is it's up to you as a software developer to make sure that it's initialized before it's used. If you use it before it's initialized, you will get a segmentation fault. And I just want to be clear that this is not undefined behavior, right? You get a segmentation fault, not undefined behavior. It is maintaining that safety aspect there. It emits a sig-sev.
Well, I mean, I understand that, but if the data is truly uninitialized, how can it detect that you're using it? It's the detection that's mystifying me.
Oh, yeah. The way that it's implemented under the hood is that there is a bool in the type, in the class that would just keeps track of that. Yep.
Okay.
You're saying this happens in the C++ code that the initialize will trigger a cycle.
Yeah.
Okay, thanks.
Exactly.
So you said there's an implicit bool. Are there any other implicit objects, and does that add too much overhead?
There are not other implicit objects. There's just the bool for this. Yeah.
So if you have some existing Rust type, that means that's not getting exposed directly to C++ because it doesn't contain this bool, right?
So if you look at the memory layout of what you're exposing in C++, it's basically you have the memory for the Rust object and then an extra byte for the bool.
Right.
Yeah.
So if you have, say, an array of like a vector of these C++ objects, they don't contain the bool, right? So you're not going to manipulate it by pointer in its current location from C++, right? Something else is going to happen so that it can be put into this form that C++ understands with the bool in the layout.
The other way, if I had a vector person on the Rust side, and that gets exposed to C++, what do I get?
Yeah, it's not doing deep. It's not going in there and adding that bool for all of the things in there.
We understand that. So anyway, maybe it'll become clear as we go on. But like, what are the implications for interop is sort of the question that I'm having here.
Yeah, I'm not sure. I haven't thought that one through. Okay. Another thing that you'll see is that the copy operations are disabled. So in Rust, generally speaking, you don't have implicit copies. The only time that you have an implicit copy in Rust is if it's if you can mem copy it to a new location and both the old and the new location are valid. And in this case, this example, it doesn't have that property because you have a dynamic string element here. So on the Rust, or on the, what is this thing called? I want to call it Zngur. So on the Zngur side, the clone method is what you use to get a copy of the thing. So on the C++ side, you're going to have a clone method. So it's not trying to imitate C++, it's trying to imitate Rust. So when you use a Rust object in C++, you're going to be calling .clone. You're only going to get implicit copies if it would be implicitly copyable on the Rust side. Methods work as you would probably expect. So we've got the name and the age method. Those end up being member functions on the C++ side. Now you'll note that name returns a Rust ref of Ruster as opposed to like a C++ ref. So let's look into that. I think that's an important aspect of this design. So basically, Rust references are different from C++ references. So any attempt to try to pretend that a C++ reference is a Rust reference is going to be fraught with problems. So the first difference is that Rust's mutable references are exclusive. You can only have one Rust mutable reference at a given point in time in a program's execution. In C++, the non-const references in C++, you can have as many of them as you want, right? So that's an important difference. The second difference is that Rust shared references, which are similar to C++'s const references, they imply value stability. If you have a shared reference to an object in Rust, you can be certain that the value of that object is not going to change, right? It's going to be stable while you hold that const reference. In C++, if you have a const reference, some other code somewhere else can change the value while you hold a const reference.
Is that like having restricts on it? I guess in C or what would be for
It's like a shared pointer to a const t.
No, it's not. Restrict is about aliasing pointers that, or references that are, if I understand right, directly passed to a single function, right? But there may be a reference from outside that function.
The third difference is that Rust references can be so-called fat, which means that it encodes additional information besides the pointer to the object. For example, like dynamic dispatch, virtual functions, this kind of thing, they store that in additional data for some types. C++ references are always thin. If you do size up a C++ reference, it's always going to be the size of a pointer. So to account for these differences, Zngur provides ref and ref mute templates. So if you want to communicate that you have a Rust reference, then you use one of these templates. You don't try to use a C++ reference. So any type that you put in your interface in your Zngur file, you're going to get a specialization of the ref or the ref mute, the ref and the ref mute template. And the specializations include the pointer. If it's a dynamically sized type, it'll have the additional metadata. And the specializations also stamp out every single member function that you have for your underlying type. So if you use a Rust reference, you're not going to use the arrow. You're just going to call the member function with the dot. And we'll see an example of that in a second. Okay, so here we are just creating our person in C++ using this interface. There's the new underscore because it's a keyword in C++, so it's smart enough to know to add the underscore there. And let's say I create a Rust reference to this person. And remember, a Rust reference, this one is like a const reference in C++. So the C++ code needs to uphold the guarantee that P is not modified while pref exists. So if you're writing the C++, you need to uphold this guarantee. Which, again, if you're doing C++, it's already a best practice to not do this anyway with C++ const references. But here it's a requirement if you're doing this Rust stuff in C++.
And this is not enforced by Zngur?
Could be.
Well, Zngur, no, Zngur can't enforce this. I mean, well, I guess it could enforce it maybe at runtime dynamically, but yeah, no, it doesn't. Okay, so pref.age, as you can see, you can just call methods on this directly. And this is just like Rust. If you have a reference to something in Rust, you can just call methods with dot just fine.
So I think you could actually enforce this statically in C++, but if you use like a std move, that actually doesn't get moved from. It just makes the compiler think it's moved from, so you can't use it. Like the compiler will warn you if you try to use it outside that scope. Afterward.
Well, getting a warning isn't really enforcing it statically, right?
Well, if you make a warning as error.
And you'd have to put it back somewhere.
Yeah, so then you have another no-op move that's like, yeah.
Yeah,
I don't know. Maybe you could hack something up, or you could just extend the compiler to add new warnings for Zngur stuff directly. That's all possible.
So if this stuff isn't actually enforced, aren't we sort of almost intrinsically going back to like an unsafe paradigm?
Oh,
You're in C++.
You're in C++.
So it's still we're still kind of assuming this.
Right.
Isn't.
Yep.
Which makes me like think that this whole bool uninitialized thing is a poor design trade-off. Because like this is an attempt to put like a little bit of safety in one particular part of C++, and in general in C++, we don't want to have things uninitialized. We want to force you to initialize them. So I would have had to, made default, uninitialized constructibility and opt in and left it unsafe for that case. Because it's costing a lot in terms of interop, the ability to actually reference the Rust object as it is in memory, right? Because the Rust object doesn't have that bool in it.
Yeah, I mean, it's definitely a design trade-off there. I don't know what the right answer is. I just know what Zngur does.
Yeah, not a criticism of you.
So I think you have to have the bool to get correct destruction semantics. So using it for initialization is just because it's already there.
That's a good point.
That's a good
Because you can manually move it.
Because Rust has destructive move that cancels the normal destructor. C++ doesn't.
Yeah.
That's a good point.
Yeah.
Yep.
You.
And you can make the destructor no up to and require that you call drop once you're done.
Oh yeah, you could do that. Yeah. Make people do it all explicitly in C++.
Make Rust really unsafe to use.
Yeah.
Yeah. So moving on to the ref mute. So here the C++ code must uphold A, that there is only one ref mute referencing P at any given time, and B, P may only be modified through pref. Right, so that's what you got to do. Okay, so this is a more minor thing. You do additionally get these static functions generated for all of your methods. And you can see that they basically take in self or whatever directly. The reason that these are provided is just for consistency with using Rust in Rust. Because in Rust you can call a method, just fully qualify the name of the method, and then pass the object as the first parameter. That works just fine. So they just want this to carry over to
This is the answer to VAC.
What's that?
This is the answer to VAC. When you access a VEC of person, you're getting a ref Rust crate of person, and you have to go through these static methods to use it.
Yeah.
It's how you deal with the layout difference between
Rust
crate, Rust person, and Rust crate, C++ person.
That sounds right.
Yep. Okay, so now this layout thing. What's up with that? So this is declaring the size and the alignment of the Rust type. If you're going to create a Rust type on the C++ stack, you need to know the size and the alignment. And the way that Zngur works is it's not parsing any Rust code. You just have what's in the .zng file. So this information needs to be provided. So when I first saw this, I was like, oh shit, I get these numbers wrong. Like I'm hosed. It's like undefined behavior all over the place. It turns out it's not that bad because when you run Zngur, it does create that generated.rs file. If you try to compile that file and these numbers were wrong, that file will fail to compile and say, hey, you put in the wrong numbers, here are what the right numbers are. So if you want to find out how to get this information, the clean way is if you're using a Rust IDE, you just hover over the type and it'll tell you what the layout is, and you can get it from there. But to be honest, what I did when creating this presentation and when I messed with it, I just compile it and see it fail and then use the error message to figure out what the right numbers are.
Can those numbers change based on target platform?
Probably, yeah.
But then if I have to commit it to do I need a different Zngur file for every target platform?
Yeah, maybe you want to. I mean, this comes back to like the generation of the Zngur file.
Yeah. I'm liking that more and more.
So do they have to be literals, or can you use expressions of some sort, use it with constants?
I don't know for sure, but I would assume it's just literals. Okay, so that's using Rust from C++.
So how does Rust methods that take a owned value do? So a consuming method. Does it mark it as art value reference on the C++ side, or how is that represented?
I didn't experiment with that, so I'm not sure.
You have one on screen. String is a consuming method. How did that one go to the C++ side?
On the new side, you're passing string.
It had to be an R value reference.
Yeah, I don't remember.
Presumably, the type could be non-copyable, and therefore, Rust has to be able to take ownership, and the bool needs to be cleared.
Oh, that's right. Yep.
So that it isn't destroyed again.
Yep, that's how it has to be. Okay, C++ to Rust side. We're going to expect this to be a little bit more complicated. So you're going to need some adapter code for most things that you're exposing from C++ to Rust. And the C++ object model, for reasons we've already talked about, isn't directly representable in Rust. So let's take, let's do the simplest thing. Let's expose a C++ function in Rust. So here we have our Zngur file, and we have a function just like we had before, except we wrap it with extern C. That's the only thing you need to do, is you need to say, this is what the signature should look like in Rust, and this should be implemented in C++. On the C++ side, in generated.h, you're going to get that function declaration, and it's put in a Rust exported functions namespace. And then you're responsible to fill out that function. You need to implement it in C++, and we already know how to do that, right? So in this particular example, we have older, which takes in a reference to a person, and it returns a new person with the same name, but with the age 5 years older, right? So that's stuff that we learned before. That's just using Rust from C++. So not too bad. But what you won't see is like creating something like that where you can take an existing C++ function unmarked and have that exposed to Rust. You have to have the Rust signature in order to be able to expose C++ to Rust. Which you can see why you're going to need that anyway, right? Like, especially if like the C++ throws an exception, you want to catch that exception, you want to turn it into a result type for the Rust side, all that stuff. And I do think that there's actually a pretty nice opportunity here for someone to make a C++ library that makes this easier, right? To automatically translate exceptions into Rust results and things along those lines. But that's completely independent of Zngur. Okay, what about exposing a C++ object to Rust? So here we have in C++ a struct, and it has a single data member called data, which is just a std vector of Rust persons. Okay, so this is a C++ data type, which uses some Rust data types inside of it. And here we're using this. We just create a new object in C++. We push back a couple of different people, Beyonce and Jay-Z. And then we call print_people, which is a Rust function with the C++ object. And this Rust function, you can see on the right, is just, print_people is the name of it. And it calls p.len to get the length. It calls p.index to get the index of, or to get the value at index I of that underlying vector there. And to expose this print_people function, which is written in Rust, and you want to use it in C++, we already know how to do that in Zngur, so that's the Zngur code for that. Cool. So how about exposing this object? How do we do that in Zngur? So we're going to start at the bottom right here to see how that works. First, we had a .len and we had a .index. So we need to expose that to Rust. And we do it very similar as we did before. We just take those function declarations. This is an impl for the people object we're exposing in Rust. And we wrap it in an extern C++ to make it clear that these are being implemented on the C++ side. And then the implementations themselves on the C++ side look just like this. What you're getting is a reference to the Rust crate people, okay? That's the Rust version of people, which is distinct from the C++ version of people. You're basically gonna have two, the Rust one and the C++ one. And once you have that object, you can call .cpp to get the underlying reference to the C++ people object. So we have p.cpp to get the C++ version, then you call .data.size in order to be able to do that. So that's what that looks like. And the generator.h will give you the signature, and you need to fill out the implementation for this thing.
So p.cpp could presumably fail because the Rust crate people thing might not actually be part of the C++ people?
.cpp will never fail.
Oh, okay.
So whenever you initialize the Rust version of people, it's always being initialized with a C++ reference, in this case, to a reference to the C++ people. Okay, we'll see how that works in a minute, but yeah, just assume that it always exists. And the index function works pretty much in the same way. You see we're calling p.cpp to be able to get the C++ reference. But one thing to note is that if you give it an index which is out of bounds, we're calling abort. You don't want to expose undefined behavior to Rust. So none of this stuff is marked as unsafe. So we're going to want to make sure that we do this check here and have some defined behavior for when things are out of range. And then it just returns p.cpp.data of index. Okay, so now for the object itself. So on the Zngur, we say type people. So this is the Rust version of this type. You put this special directive underneath to say this is a C++ reference to people. And then you also need a little bit of boilerplate in your Rust code to say pub struct people, and then you pass in Zngur CPP opaque borrowed object.
And that's not generated.
That's not generated, no. Now, because we're exposing it as a C++ reference, in Rust, you'll never be able to actually create that Rust people object. The only time you'll ever see it in Rust is a reference to it. And it's a reference to something which lives in C++ somewhere. It's on the C++ stack, or it's in the C++ heap, something. It's in C++, and you just get a reference to it in Rust. And there's no way you can get the actual underlying object from the reference. You just always have a reference. So this is very efficient, obviously, because we're just talking about a single pointer here. It can be on the stack or on the heap, but C++ stack only. That's one way to do it, right? And then you can use it otherwise just normally in Rust.
So by get the underlying object, I mean, a Rust reference, points at some memory. So I think, do you mean you can't move from it? What exactly does it mean to not be able to get the underlying object? You can't declare one.
Yeah, you can't create one. You can't put it on a Rust stack.
You can't give the ownership to Rust.
Exactly.
Okay, got it.
Okay, the other alternative is to use the directive CPP value. And so we see some of the changes over here. So on the right-hand side, you see Zngur instead of saying CPP ref, you actually have to provide a layout for this because you're going to actually have objects of this type in Rust. We're saying CPP value of people. I'm not really sure what the 0 is there for. It's needed, but I don't understand its motivation. And then you declare that there's a constructor for it called Zngur CPP opaque owned object. And then in your Rust code, you change your boilerplate a little bit to say CPP opaque owned object as opposed to borrowed object. And on the C++ side, we need a way to create this in Rust. So we add a new function down there. We implement new like this. You see we're creating the Rust people object. We're passing in this Zngur CPP opaque owned object ::build thing. And what that's doing is an in-place construction there of the C++ object. And this is dynamically allocating it, right? So there's really a new happening when that build function is being called. So on the Rust side, you can use it like a Rust object at this point. And you won't really be able to tell the difference. So you can say let p equal people new, you can call p.len. But the one thing to keep in mind is if you're doing this, is that this object, the C++ object is living in the heap somewhere. It's not actually living on the on the Rust stack. So when you're calling functions with p and all that kind of thing, it's doing the memcopy moves of that, not the C++ object, which is underneath. Does that make sense? It's a bit complicated.
It's a box. It's moving the pointer around.
Yeah.
Yeah.
Okay. We'll talk a little bit about traits. The heavy stuff is over. Now it's a little bit more light. So we see that we have a function index over here for our people object that we're exposing in Rust. There is a special trait in Rust called index. If you implement this trait, then you can use the square brackets as opposed to .index. So the question is, how can I conform to this trait or implement this trait for my C++ object? And it turns out this is pretty easy. You just say that you want to implement index. And index needs to have a IDX type, which is like, what are you indexing it with? It needs to have an output, which is saying like, what is the result of the index operation? You pass all that stuff in your implementation block in your Zngur code. And then in C++, you just need to change that function signature to do the thing which says I'm implementing that trait. That's it. Otherwise, the code remains the same. So you can implement Rust traits with your C++ objects. Or no, wait. I forgot which direction we're going in.
You said it right.
So Zngur is generating C++, which you don't want to write by hand. It's messy. But we also said you really want to generate the Zngur.
Yeah.
I forgot what my question about that was, but
Theoretically.
yes, I remember. Do you want this intermediate representation so that you can custom tweak it? I mean,
no.
Why do we want the Zngur file ultimately?
Yeah, I think that's a great question. There are two aspects to the answer. So one aspect is you could say, hey, I want to generate, like if I'm exposing Rust from Rust to C++, I could say, hey, just take this crate, everything in it, generate the Zngur file for it, and I'll just use it in C++. That's totally possible. There's no reason why that can't happen, and that would be a very useful thing. And I think that the author of Zngur has like a prototype implementation to do exactly that. However, that isn't going to be sufficient always, because the type system in Rust is open-ended, right? I could want a Rust tuple of these things, or I could want a vector of this type or that other type. And so in some sense, you need to know what you're going to be using in C++ in order to be able to know what goes in the Zngur file. You can't even if you say I want to use everything in this crate, like that's actually open-ended, right? Because there's an infinite number of types you can derive from that.
So I think the answer is yes. You might want to tweak it, like throw out some things because you don't want to represent them, or I mean, what you talked about, I think, is a subset, right? You might want to expose a subset. That's one kind of tweak.
Well, no, I mean, if I say expose everything in this crate, it can say, okay, here you've exposed everything that can be exposed that isn't like dynamic, because you can build types on top of other types.
I mean, your person contained a string. That's a type built on another type. I'm not sure what you mean
I'm
by
talking more about.
I think you're talking about generics.
I'm talking about generics. Yes, I'm talking about like.
Generics are dynamic.
It's not the generics are dynamic. It's how do you expose a generic? You have to expose something with a concrete signature. So.
Okay.
Right.
Sure. Well, I mean, yeah, you could, because of monomorphization in Rust, it seems to me that you could expose a C++ template for your Rust generic in principle.
I'm not sure you can do that with the Zngur file.
Yeah, I don't
Because
know. I'm interested.
It's all like concrete types is like how this thing works. So one thought related to making this more automated would be is if you had an IDE where you open up that Rust namespace and it automatically looks up into like what's possible in Rust for that. Mm-hmm. And then based on looking at what you're doing in your C++, then you can generate your Zngur file based on that. That should be a complete solution.
So as someone who doesn't know how to use Rust but may want to try, this signature you have on the left-hand side looks quite complicated to write. Is that same signature part of the generated C++ header?
Yes.
Okay, so then that can just be copied and be implemented. Okay,
yep,
great.
Exactly. Okay. So now on the left-hand side here, we're just seeing the print people function now can use the index operation because we've implemented that trait. So we have the square brackets. Zngur also provides this idea of dynamic traits that can go across. So in Rust, you can create a trait for something, but you can also make a dynamic dispatch version of that trait by putting dyne in front of it. And that gives you something like abstract base classes in C++. So I'm not going into details of like how you actually generate this, but Zngur, you can say, hey, I would like to expose this dynamic trait to C++, and it will generate in generated.h an abstract base class that you can inherit from. And then you inherit from it, and then you can call Rust functions that expect a dynamic dispatch version of a trait. And that works, and it's kind of cool. Okay, so that's all the basics here and the advanced stuff. Now I'm going to shift to a concrete example. But before I go to the concrete example, are there any other questions people are holding, comments? Yeah.
So you keep talking about a Rust stack and a C++ stack. Are those stacks like actually interleaved, or like how does it implement two different stacks?
Oh, it's the same stack.
It's the same stack. It's just it's the stack frame would be a more concise.
Yeah, what he means is, was the stack frame created by some Rust function or some C++ function? That's all.
Yep. Okay, here's the example. PNG parsing from C++. So if you wanted to parse PNG from C++, right now the most typical way that people do it is they use libpng. If you use libpng, you can be aware that it does have CVEs, right? All the bugs have been fixed, but there are 75 vulnerabilities that have been discovered in libpng, and most of these are memory safety issues. And there's no guarantee that libpng isn't going to introduce a new issue with updates. There's no guarantee that there isn't already an issue in there just lurking. We just haven't discovered it yet. You can do that if you want to use libpng. Or you can use a Rust version of this thing. So there's a Rust library called PNG, and this PNG library has no unsafe code at all in it, which means that you get a compile time guarantee that there are no memory safety issues in this PNG code, right? That's a really strong statement. And so if you're writing software which is going to be used by hundreds of people, you can insulate them from having a memory safety exploit by just using that one on the right as opposed to the one on the left. I think it's pretty important. So here's what the C++ code looks like for using that. The first thing that we do is we create a Rust str, which is like a string, like the Rust representation of a string. And this is just our file path test.png. Then we need to create a PNG decoder object. And on the right-hand side, you probably can't read that very well. This is just documentation, like the front page documentation of the Rust PNG library. It was essentially just transliterated over to C++ to be able to use it. So we create a decoder object. It requires a file object as an argument. And you see some unwraps in there. That's just saying that it's returning a result object, and I'm just saying if there's an error crash, and otherwise just grab the result.
Did you have to write the Zngur for decoder and file?
Mm-hmm.
Oh, so stdf has file you had to write the Zngur for.
Yes.
Okay.
We call the read header info function on the decoder. And again, this returns some kind of a result type, so we're just going to use .unwrap to get the result out of it. And then we have the width and the height, which you can see in struct info. These are actually fields, but on the left-hand side, we're calling functions. And this is a limitation of Zngur. It doesn't expose fields. It only exposes functions. So we're going to have to do something in order to be able to add the width and the height functions that we're using here. So let's do that. The way that you do this in Rust, to add, there's this thing called an extension trait, and you can use it to add more member functions to a given type. And so we create our trait called PNG info ext. We have width and we have height, which return U32. And we make an implementation of this for the PNG info object in a very straightforward way, right? Now, it's a question for me personally whether or not it'd be worth it for Zngur to expose fields in some way so that you don't have to write this boilerplate, because it seems like it would be possible, but it needs more thought. Okay, so now let's look at our Zngur file. So for str, we're going to have type str on our Zngur file because we're using it. Here you have well-known traits, question mark size. I didn't go into detail on this, but this is basically just saying that this is one of those fat pointer types with str in Rust. We need to have our file object with its open function. So we know how to declare that and get the right layout. It returns std.io results instantiated with std.fs file. Here we expose that type, and we're using an unwrap function, so we expose that function on that object. Now our decoder object, we need to create this new function here, so we expose new for that. And we also need to expose read header info. And that returns a result, so we need to make sure we expose the result as well as its unwrap function. And then we have the width and the height functions. And that's it. Yep.
Back to the layout. You said on the Rust side, that's validated during compilation.
Yep.
That's ignored on the C++ side.
Yes.
That does not translate over at all.
Oh,
because
or-
that's not providing. Is that size also equivalent to what is on the C++ side, or is that purely a Rust invariant that is enforced?
So on the C++ side, when it's creating the C++ version of that object, it needs to know how much memory that object is going to take.
The Rust part of the object.
Yeah, the Rust part of the object. It needs to make sure
Right,
that space.
but it's just the Rust part of the object. So that size is purely a Rust implementation detail. It has nothing to do with the C++ side, because they can add additional fields, like the bool, for example.
Yes.
That's not going to include the other
Correct.
semantic metadata that is needed to enforce invariants.
Yep, exactly.
Since you've got the width and height access highlighted, I think the problem with exposing fields directly to C++ is that you would have to know how to generate C++ layout for the struct that matches Rust, and C++ layout rules are compiler specific, platform specific, target specific. Interesting. So it might be a potential extension of C++ to give precise layout rules or something like that. And as we have discussed, good luck getting the C++ committee to accept any features that support interop with other languages, right?
Yeah, I don't know.
Somewhat flawed, but Rust does have the ability to declare a struct as having a C layout representation, which and then you can add all of your methods to it. That would give you a more stable interface into the C++ and potentially allow you to auto-generate the hash layout, although Zngur doesn't have that capability.
But the layout rules don't apply once you make it a C++ class, and it's going to have destructors.
But you don't make it
Oh, I see.
Yeah.
The Rust part could be C compatible potentially. Yeah.
Right.
I see what you mean.
Yeah. So I almost think that you could get to the point where you could auto-generate the Zngur in a portable fashion from Rust code, which has information about both the C layout for the object and the Rust.
Yeah.
And the Rust thing. So it could be even a fancy Rust macro that might be able to do that. But
I don't think you can still even get direct access to the field. You would have to hop through the subfield that is the Rust part. And what's the point? It's just syntax, right? This could all be generating inline functions.
Yeah, I'm actually more worried about the hash layout.
I don't think you would want to force the C. You pessimize whatever Rust is going to do. By saying you need to follow this particular ABI, in Rust, you're saying it has to be laid out this way, rather than the opaque Rust implementation, which just says we're going to lay it out the way that we want to lay it out.
Well, yeah,
and that would be the classic interop pushback of don't pessimize me for laying out the way that I want. Now maybe that doesn't matter. I mean, it's a performance question of does it actually matter?
At the same size, you can extract from either side, from the C++ side. If you were exporting the C++ object, you could extract the layout for the C++ object as metacode in C++, and you could do the same thing to extract the layout as code inside of Rust to fill that in a portable fashion. How you get that going in the build system and everything, I don't know. But just looking at the Zngur docs, it's like that layout is tied to the compiler version you're using on Rust and the platform you're executing on with your C++ code. And it's hard-coded.
Well, it's just tied to the Rust side, right? To your Rust platform.
If you're only going that direction.
Yeah.
If you're going,
which we are, because we never actually create
a C++ object on the Rust side.
Yeah.
Okay. I see. Yeah. Okay.
Cool. I saw some more questions over here. I'm happy to take them now because. Yeah.
When you create a type in Zngur, that then creates the type in the C++ code and creates the type in the Rust code, correct?
No.
Okay, because I was working under that assumption because I was then going to ask how that works when you create a type in Zngur that already exists on the Rust side.
Yeah, when you put a type in the Zngur file directly like this, the type is already on the Rust side. There's nothing happens on the Rust side.
Well, but the Rust side can see the C type, the C++ compatible type, right? You can't create one, but it manipulates references to it. So that is a type on the Rust side. It's the same, right? They're related, right?
Well, let me just be clear. Like if you just put a plain type, there's only a type created on the C++ side. If you're doing a CPP underscore value or that kind of thing, that is creating a type on both sides. Yeah.
CPP value is something you put in your Rust code, right?
CPP underscore value is something you put in your Zngur file.
Oh, okay, I see. So this tells you whether you want to be able to access the C++ version of the Rust type from the Rust side through a reference. I'm sorry.
I wasn't able to fully.
Interop is hard.
It is hard.
It's hard to talk about. And you probably already covered it, so let me not hold up the presentation.
All right. All right. We'll take this question and then we'll move forward.
Yeah, it looks like there's a lot of stuff to be generated in the C++ side. Just playing around with the idea, do you think reflection will help by reducing the amount of tooling, like the third-party tooling, where we can maybe have a magic function in C++ that says make this as Rust-friendly as possible for me, and have it some way so that it can expose some kind of facility where another program can come in and read some specific identifier that we left in, and so it's more C++ friendly.
I don't know, but I'd encourage you to explore that idea and see what happens. I don't know, I'm not sure. Okay, so putting this all together, this is my build.bat file. I'm running on a Windows computer here. This is what I needed to do to build this. I just called Zngur generate on main.zng. That generated the .h, the .cpps, and the .rs file. I ran cargo build to build the stuff on the Rust side. And then I used Clang++ to build the actual executable. And that was it. Like, that was not complicated at all. And you see in the Clang++ line, I do mention the generated png underscore example.lib, which was generated from cargo. And then there's a couple other libraries that it depends on, like some OS specific stuff. Okay.
Do you need to configure anything in cargo to make sure that it generates that lib, or is it just automatically generated by cargo when you make a build?
So before I ran cargo build, I had to do cargo init to create a new crate, and that generated a lib.rs file. So that extension trait lived in lib.rs. And then the other thing I needed to modify was the cargo.toml file to say I'm generating a static lib.
Yeah. Probably had to add the dependency on Rust lib PNG or whatever.
No. Oh yes. Yep, exactly. But notably, I didn't have to add a dependency on anything related to Zngur.
Yeah.
Yes.
I have two questions about the main.zng. Could you do, like, if you split up your Zngur across multiple files, could you have Zngur generate, foo.zng, bar.zng, etc., or is it always one file?
So the Zngur executable right now, it always creates generated.h, generated.cp. You don't have an option to change the output of it. The Zngur library does have more access, so you can say okay, I want to generate this here, this there. There might be some opportunity for things, but what comes out of the box is just one Zngur file. That's all I get.
Okay. And then I assume that you'd want to, you wouldn't run the generate step as part of your CI, right? Because you have to fill out the generated.h, gener.cp files. You have to fill those out with
Oh,
human.
well, those you don't actually fill out, right? That you provide your own .cpp file which implements what the header
Okay.
declares. Yeah.
Okay, but still, you have to. You're not doing that in your CI. You're like.
Right. So you're like impl.cpp. You would check that in.
Right.
You would check in your Zngur file. You wouldn't check in generated.h, generated.cpp, or generated.rs.
Don't commit generated files, please.
Okay, I see what you're saying.
Okay, so just kind of looking back at the PNG example, kind of a retrospective here. So to do this, it took about an hour for me to write this example code and the Zngur file and all that kind of stuff. And doing safe PNG parsing in an hour, I think, is a pretty cool thing. I don't think that's not typical, but the tech is there now. I found that adding a Rust dependency was easier than adding a C++ dependency. PNG, that library depends on a whole bunch of other things, and those depend on other things. And I didn't have to do anything. Cargo took care of all that for me. So that was a pretty pleasant and a little bit surprising experience that it's easier to add Rust to C++ than C++ to C++. Anyway, I was fairly happy with how the C++ code looks. I got the feeling that it's kind of like when you adopt a framework that somebody provides, like Qt or something like that, and it has its own way of doing things. That's the kind of feeling when you're using Rust libraries in C++. You've got this result type, so you gotta, kind of learn how to use the idioms of the language. But it wasn't terrible. I found it to be pretty good. Although I do think that there's probably opportunity, like again, for like a C++ library, which wraps some of this stuff or makes some of this stuff a little bit easier. That could even improve that. I didn't integrate this with the build system like CMake. That would take more time than the 1 hour probably. But I don't anticipate any major obstacles to do something like that. I think they handle generated files pretty well, and running external subcommands like cargo build would work. So I'm gonna wrap it up, and we'll probably have time for just a couple questions. I think there are many good reasons to adopt Rust right now. It's got a good feature set. There's a wider demographic shift that is happening. It has a lot of safety improvements when you compare it to what C++ has. And I think Zngur makes for a pretty great C++ Rust interop experience. I would say it's not seamless, right? I mean, you can see the seam. There's definitely hope to automate a lot of that stuff, because all that stuff seems pretty automatable with some tooling work. But yeah, I mean, I thought it was pretty good. I felt like it was ergonomic on both sides, actually. When you're using the C++ code from Rust, that also has a pretty good experience. And so now I feel like the door is open for using Rust libraries in C++, if that's something that works for use cases. So that concludes my presentation, and now I'll take some questions.
I thought there was a type from Zngur that you used. So does this mean that Zngur does provide its own runtime of some sort to fill things in? I think it was Zngur CPP borrowed object type or something like that. So there is some sort of implied API that is infrastructure that's supporting all of this, that is tied to what version of Zngur you're using.
So that type is provided in the generated.rs.
Got it. So everything that generated RS is a complete self-contained piece of code. There is no third party.
Yep.
Yeah, I actually did this, but are there any examples of large enough code bases that use Zngur, C++, Rust integration? So is it like a mature piece of tech or just a proof of concept?
I would say it's somewhere in between. I don't think this has been used at scale yet, but it's actively developed. Like every time I've found an issue, the author just solved it really quickly. So it's very actively maintained, and I think they're just looking for like more usage experience, and that'll hone it and make sure all the sharp edges are kind of knocked off of it. Yeah.
Is there any anticipation to provide features to more smoothly handle generics and templates?
Not that I know of. Yeah.
So can I address that a little bit? Handling templates from the Rust side is generic interop is heavily complicated by the fact that Rust generics are separately checked. So there is no like type checking after instantiation phase, right?
Right.
So if you want to use a C++ template from inside of a Rust generic, there's no way for it to decide, oh wait, that's illegal for this particular set of Rust parameters.
Right. I mean, you could do something with concepts and whatnot, right? The core insight here is that it's easier to generate C++ interfaces from Rust than it is to go the other way. So like you have some sort of restricted subset of C++ certainly, and you'd also have to have a separate linking step to make sure that you actually generate you actually instantiate the templates that are necessary from the Rust side. But I was just curious if there's like any sort of direction or anything about that whatsoever. I recognize it's a difficult problem. I was just curious if there's any.
The type checking problem is not one that I mean. I've been thinking about how to do this same problem for Swift and Hilo for a long time, and the type checking problem is not one that has any obvious solution, including using concepts. C++ concepts are not strong enough to do this.
So I'll take one more question over here.
So if the Zngur file generated code is completely self-contained, what happens if I have one component in C++ that is using one Zngur file and another C++ component that is using a different Zngur file? Can those two talk to each other at all, or it's totally independent?
I think that as it is right now, the tech, I don't think it provides a way to even customize the namespace of your generated.h file. So they'll just like conflict, right? But in theory, if you made a like a way to like put what your namespace is, then they would be completely independent of each other and would not interoperate at all. It's like two different worlds. So doing this at scale with that kind of thing, I haven't seen that demonstrated yet. Okay, that is it. Thank you all.